Okay, so hello everyone. In this video, we will see concept of overlay and very important questions based on contiguous memory allocation, which we have discussed in our last lecture. So in this video, first we will discuss two important questions, and then at last we will see concept of overlay and a question on overlay also. So let's start with first fit and best fit question. The question is asked in GATE exam about allocation algorithm, specifically first fit and best fit. We have request from various processes: 300 KB, 25 KB, 125 KB, and 50 KB. Now these requests need to be satisfied, and we will examine how first fit allocates memory to various processes and how best fit allocates memory to the same processes. In this question, we are given the status of main memory at a point in time. Some portion are like already occupied by existing processes. These represent memory and that's are already allocated. We have two holes available, one hole of 150 KB and another hole of 350 KB. As we know, dynamic partitioning, when we allocate memory to the processes, we allocate at a runtime. When a process requests memory, we allocate it immediately. The problem that occurs is that many holes get created over time. Here we already have one hole size 150 KB and another hole of 350 KB. Now we have process request is in order. One process of 300 kilobyte, then 25, then 125, then finally 50 kilobyte. Then these must be processed in the sequence. Now moving forward to the solution, first fit algorithm. Let's solve this first with the first fit. How does first fit behave? The first process is 300 kilobyte. According to the first fit, whenever we find the first location big enough to hold the process, we simply allocate there. When I find the first portion where I can accommodate the process, I place the process there. And so what is the size of my process? 300 KB. Can I accommodate 300 KB in 150 kilobyte? No. 300 process cannot be fit in this hole. But can we put a 300 KB process in 350 kilobyte hole? Yes, because the hole size is larger. So there is no problem. Let's call this process P1. When process P1 of size 300 KB allocated in a 350 KB hole, so it occupies that memory. But here is the first important point about dynamic allocation. When we fill a hole with some process, the remaining partition is also a hole. In the 350 KB hole, if I fill 300 KB, how much remaining space do I have? 50 KB. So a 50 KB hole remains. The next process is P2, like say 25 KB. According to first fit, where do I start searching again? I search from the beginning also. So from the beginning to find where I can place the process, the first available slot is 150 KB. Can I put this process in 150 KB? Yes, because the process size is the only 25 KB. So it can easily be accommodated here. After accommodating P2, the remaining portion is also a hole with size 125 KB, which can be used for future processes. The next process is P3, 125 KB. According to first fit, I start scanning from the beginning. When I find the first location where I can put the address, I place it there. The process size is 125 KB and my first available hole size is exactly 125 KB. So I can fit P3 entirely here. This hole is completely filled with P3 process. The last process is P4 is 50 KB. The previous space are all occupied and I have only 50 KB space remaining. The process size is exactly 50 KB. So it fits perfectly here. According to first fit, it works properly. All four processes that were requesting memory have been allocated space in the main memory successfully. Now best fit algorithm. Now let's check the same question with best fit to see whether it works properly or not. We start with the same diagram, one hole of 150 KB and another hole of 350 KB. The first process is 300 KB. What does best fit check? When we put a process in some slot, first the slot size should be such that we can accommodate the process, but the key principle is that after putting that process, the remaining space in that hole should be minimum. So if we put 300 KB in a 150 KB hole, no, we can't, because it won't fit. So where can we put? Only in the 350 KB hole. Let's say we accommodate P1 here. So P1 is allocated in 350 KB hole, leaving 50 KB remaining. The second process is P2 is of 25 KB. I can accommodate 25 KB in 150 KB hole also. If I fill 25 KB here, the remaining portion size will be 125, which is quite large. But if I put this in 25 KB in the 50 KB remaining space from the previous allocation, then the remaining portion becomes 25 KB. Since the remaining space here is the least, and this is the technique of best fit, when we put the process, the remaining space should be minimum. We place P2 in the 50 KB slot. Now next comes P3, which is 125 KB. Obviously 125 KB can be accommodated in the 150 KB hole because the other location only has 25 KB remaining. So P3 is accommodated in the 150 KB hole. The remaining space becomes 25 KB. At this point, we have 25 KB space remaining in one location and 25 KB space remaining in another location. Now comes the 4 process P4, which is of 50 KB. The process size is 50 KB, but we have 2 slots of 25 KB each, totaling 50 KB available space. However, can we put the process here? No. This is because first fit, best fit, worst fit all work under contiguous memory allocation. In contiguous memory allocation, we cannot span a process across two separate places. We cannot divide and place a process in multiple locations. Even though we have 50 KB total space available, 25 plus 25 is equal to 50. We cannot place this process because of the contiguous memory allocation requirement. This situation is called external fragmentation. Even when using first fit or best fit, external fragmentation can still occur. So according to our analysis, first fit is working properly, but best fit is not working properly due to external fragmentation. Now let's also solve this with worst fit. Worst fit works exactly opposite to best fit. We put a process in that slot like such that after putting it, the remaining portion should be maximum. In best fit, it should be minimum. In worst fit, it is maximum. So starting with holes of 150 KB and 350 KB. For the 300 KB process, I can only put it in the 350 KB hole. For the 25 KB process, if I put in the 150 KB hole, the remaining portion is 125 KB. If I put in the 50 KB remaining space, the remaining portion is 25 KB. Since worst fit wants maximum remaining portion, I put the 25 KB in 150 KB hole, leaving 155 KB remaining. For P3, 125 KB, I easily allocate it in the 125 KB remaining space. For P4, like 50 KB, I have exactly 50 KB space available, so I allocate P4 there. So worst fit and first fit works properly in this question. Now moving forward to another question, memory allocation with time constraint. This question was asked in GATE for 2 marks. It's about memory allocation with a new concept. Usage time, we have 8 jobs with their request size and usage times. For example, J1 needs 2 KB space in RAM and will use it for 4 time units. The question asks us to calculate the time at which J7 will be completed using the best fit algorithm. The request must be fulfilled in sequence from J1 to J8. Let's solve this step by step using a timeline approach. We will assume all jobs arrive at time 0, but they will placed in the RAM one by one according to availability. Now timeline solution. At time 0, J1 needs 2 KB memory. According to best fit, when we put a process in memory, the remaining space should be least. Among the available slots, 2 KB, 4 KB, 8 KB and 20 KB. If I put 2 KB in 2 KB slot, no space will remain. It fits exactly. This is perfect for best fit since no internal fragmentation occurs. J1 will occupy this slot until time 4. Now at time 0, J2 needs 14 KB. It can only fit in the 20 KB slot since other slots are either occupied or too small. J2 will occupy this slot until time 10, 0 plus 10. Now at time 0, J3 needs 3 KB. Between the 4 KB slots, leaving 1 KB remaining, and the 8 KB slots, leaving 5 KB remaining, best fit choose the 4 KB slot since it leaves less remaining space. J3 will occupy this slot time until 2 time unit. Now at time 0, J4 needs 6 KB. Only the 8 KB slot is available. J4 will occupy this slot until time 8, 0 plus 8. Now at time 0 also J5 needs 6 KB. Now we have no slots available. No slots are currently available that can accommodate 6 KB. Now we are talking about fixed partitioning. If we were talking about variable partitioning, we can put it into internal fragmentation also. But now this is fixed partitioning and we don't have any slots remaining. So at time 2, J3 completes and leave the 4 KB slot. However, J5 needs 6 KB which cannot be fit in the 4 KB slot. Now at time 4, J1 completes and leaves the 2 KB slots. Still J5 cannot fit in the 2 KB slot. Now time 8, J4 completes and leave the 8 KB slot. Now J5 6 KB can be placed in the 8 KB slot. So J5 will occupy this slot until time 12, means 8 plus 4, because it is taking 4 and we are standing at 8. So 8 plus 4 is equal to 12. Now at time 10, J2 completes and leaves the 20 KB slot. J6 needs 10 KB and can only fit in the 20 KB slot. So J6 will occupy this slot until time 11, means 10 plus 1. Now at time 11, J6 completes and leaves the 20 KB slot. Now J7 needs 7 KB. Here is the crucial point that many students miss. At time 11, the 20 KB slots become empty when J6 completes, even though J5 will complete at time 12, making the 8 KB slots available, which would be a better fit for the 7 KB process. We cannot wait for future event in best fit algorithm. We must allocate based on current availability. Since the 20 KB slot is empty at time 11 and we place J7 there immediately, Basically, J7 will occupy this slot until time 19, 11 plus 8. Therefore, J7 will be completed at time 19. The answer is B, 19, not 20. Many students incorrectly assume that J7 start at time 12, leading to completion time at 20. But this is wrong, because we don't wait for better fits when a suitable slot is already available. Now, moving forward to the overlay technique. Overlay is a method by which a large size process can be accommodated in main memory when the process size exceeds the memory size. If the size of my process is more than the size of available memory, I can make that process fit in the main memory using overlay concept. Where do we use overlay? When the size of our main memory is less than the size of the process. In this case, we bring the process into main memory in parts. Okay, now how overlay works? When a process size is larger than the main memory, we cannot load it entirely at once. We must divide the process or program or object code into smaller parts. We load the functionality that needed first into the main memory. Now, when that functionality completes, we remove it and bring into the another partition. The challenge with overlay is that there is no automatic driver in operating system to support overlay. The user must manually decide how to divide the process or program so that when bringing in each partition, the functionality can be executed properly. This creates potential problems. It may happen that the work needed first wasn't loaded in the first partition, or since the user is dividing manually, careful planning is required. Now, overlay in embedded system. This concept of overlay is primarily used in embedded system because user control the division process. Functionality is fixed in embedded system. Main memory is typically limited in embedded system. Embedded system perform only fixed functionality like washing machine. So we can divide the process into 2-3 different functions. When one functionality completes, we bringing the next functionality. The key requirement is that when the user divides the functionality or process, the division should be independent. If one partition depends on code in another partition, problems can occur when the CPU searches for data it cannot find. This doesn't create problems in embedded system because the function or process are fixed. However, in computers, PCs and desktop, processes vary in size and numbers, so we cannot leave this functionality to the user. That's why we use virtual memory concept instead of overlay in general purpose computers. Now, overlay exam problem. Moving forward to the question. Consider a two-pass assembler. Pass 1 is 80 KB, pass 2 is 90 KB, symbol table is of 30 KB, common routine is of 20 KB, and the overlay driver is of 10 KB. At any time, only one pass is in the use. The question is, what is the minimum partition size required? An assembler converts source code into object code using two passes. When using pass 1, part 2 is not needed, and vice versa. And total size of all components is 80 plus 90 plus 30 plus 20 plus 10 is 230 KB. If memory size were 230 KB, there would be no problem. We could load everything directly, but we are using overlay because memory size is less than 230 KB. When loading pass 1, 80 KB pass 1 plus 30 KB symbol table plus 20 KB common routine plus 10 KB overlay driver is equal to 140 KB. When loading pass 2, 90 KB pass 2 plus 30 KB plus 20 KB plus 10 KB is equal to 150 KB. Since we need to accommodate both scenarios, we must choose the largest requirement. The minimum partition size required is 150 KB. If we choose 140 KB, we couldn't accommodate pass 2 which needs 150 KB. But with 150 KB partition size, both pass 1 140 KB and pass 2 150 KB can be accommodated at different times. Now, this is how we calculate overlay requirements. We find the maximum memory requirements among all possible loading scenarios, which is 150 KB. Overlay is used where main memory is limited, primarily in embedded system. So that was whole concept of overlay, and we have discussed some question on it, and that's it for this video. We will meet in next video. Until then, bye bye.